Welcome to this introductory session on interface circuits, where we explore how these crucial components enable communication between different parts of a system, particularly between a microcontroller or processor and peripheral devices. A bus interface circuit is an essential component in computer systems, particularly in embedded systems and microcontrollers. It provides a connection between different system components such as the CPU, memory, and input-output devices by facilitating data transfer over a bus. Below is the breakdown of key elements of a bus interface circuits. A bus is a communication system that transfers data between components of a computer or between computers. It is divided into several types: address bus, data bus, control bus. Address bus carries the address of the data being read or written. Data bus carries the actual data being transferred. Control bus carries control signal to manage the operation of the system components. Address decoder is a decoder that has one or more inputs for address bits and one or more outputs for device selection signals. Address decoder enables the device to recognize its address when address appears on the address line. Data register holds the data being transferred to or from the processor. Status register contains the information relevant to the operation of the input-output device. Control circuit detects the operation of the processor. The address decoder, the data and status registers, and the control circuitry record to coordinate input-output transfer constitute the device interface circuits. The input-output interface plays a critical role in facilitating communication between the processor and external devices such as keyboards, displays, or sensors. Here is a detailed breakdown of the functions mentioned. It provides a storage buffer for at least one word of data. The input-output interface typically includes a buffer to temporarily hold data that is being transferred between the processor and the input-output device. This allows the processor to continue executing instruction while data is stored in the buffer awaiting further processing. It contains status flags. These flags indicate the status of the buffer. For input operation, a status flag indicates whether the buffer is full and ready for the processor to read. For output operations, a flag indicates whether the buffer is empty and ready to accept more data from the processor. This ensures proper synchronization between the processor and the input-output device. It contains address decoding circuitry. The input-output interface includes address decoding logic to identify whether a specific input-output device is being addressed by the processor. When the processor sends an address, the decoding circuitry checks if it matches the address of the input-output device, enabling it to respond appropriately. Generates appropriate timing signals to coordinate data transfer across the system bus. The input-output interface generates timing signals that align with the bus control scheme. These signals help ensure that data is read from or written to the input-output device at the correct times. It performs format conversion when transferring the data between the bus and the input-output device. Some format conversion may be necessary. For example, in the case of serial communication, the input-output interface may convert serial data to parallel format or vice versa to ensure compatibility with the bus, which typically operates in parallel format. The input-output interface connects the processor and the external device with the different types of signals on each side. On one side of the interface, there will be a bus signals for address, data, and control. On the other side, there will be a data path with its associated control to transfer data between the interface and the input-output device. This side is called port, and it can be classified as either a parallel or serial port. A parallel port transfers data in the form of number of bits, typically 8 or 16 bits to or from device. A serial port transmits and receives data one bit at a time. Inside the interface, there is a conversation process that changes the data between parallel and serial formats depending on the type of port used. This allows devices using different data formats to communicate with the processor smoothly. The connection between a keyboard and processor involves sequence of steps for transmitting keystroke as data from the keyboard to the processor. The processor reads these inputs, interprets them, and acts accordingly. Steps in keyboard to processor communication involves many steps. Key press detection. The keyboard controller continuously scans the keys. When key is pressed, the controller detects it and generates a unique scan code for that key. The scan code is sent to the keyboard interface circuits, serial or USB. The interface converts the data if necessary and places the 8-bit scan code on the data bus. An interrupt signal notifies the processor the new data is available. The processor reads the scan code from the data bus. The processor checks its lookup table to translate the scan code into a meaningful character or function. The processor processes the key press, displaying it on the screen, executing a command, or performing another action as record. The connection between printer and a processor involves the transfer of data from the processor to the printer so that the printer can produce a hard copy. The process is similar to other input-output devices connections, but there are specific details tailored to the printing operations. The steps involved printer to processor connection or data generation by the processor. The processor generates the data. The data may be text or graphics to be printed and prepare it for transfer to the printer. The data is sent to the printer through input-output interface, which could be parallel, serial, or USB. Parallel port, the processor sends data 8 or 16 bits at a time to the printer's parallel port. Suppose it is a serial port, the processor sends data bit by bit to the printer, requiring a serial to parallel conversion in the printer's interface circuit. USB port supposed to be used, the processor sends data packets using the USB protocol. The printer interface circuit receives the data and converts it if necessary. The interface also manages control signals to ensure data is correctly synchronized with the printer's operation. For a parallel port, control signals like stop and acknowledge message the timing and coordination of the data transfer between the processor and printer. The printer controller sends an acknowledgement signal when it receives and processes each byte of data allowing the processor to send the next byte. Printer controller interrupts the incoming data, converting it into printing commands. It also handles formatting commands such as line breaks, margins, and font selection. The printer uses the processed data to physically print the document onto the paper. This involves paper feeding, print head movement. Thank you for watching.